rewind or reset, whatever the phrase is, this section. So in a little bit more formal, hopefully a little bit more obvious way, we're going to tell you what the fundamental theorem of line integrals lets us do. If you have got a conservative field f, pq, right? P is a function of x and y, q in this case is a function of x and y, and you want to find the line integral of this version, right? The f dot dr version. The fundamental theorem of line integrals says that the answer is little f of b take away little f of a. The function little f, called the potential function, has this property, that the gradient of this guy is f. And the guys I'm calling little a and little b, around what I called them last time, are essentially the position vectors. Okay, that means the coordinates of your start and your finish point. So finish, take away start. And that means then that as long as you're a conservative field, we don't care what route you take, we only care where you start and where you finish. So I think this is called a potential function because it's like the difference between a start and a finish, right? The potential is the number that is between them, right? Because we know a line integral is a number, right? So that's pretty much what the fundamental theorem says. This little guy at the bottom is how do we check or see if a field, a vector field, is conservative? And we just check that does this derivative equal that? So first guy I'm going to do is a version of 5. Seems to be a good place to begin. And we are going to be finding the line integral f dr. Oh, I think that was a precedent, where f is the function x squared y cubed and y squared x cubed. There's no need for these functions to look particularly like each other. This one just happens to do it. The curve C is a space curve, and it's described as t to the 4 take away 2t, comma 3t squared minus 1. And the curve starts at 1 and it finishes at 2. So it's basically what I've got there, right? Now, first guy I'm going to go hunting for is A and B. A is the coordinates of the start position. So if you plug 1 in here, you get 1 to the 4, take away 2 lots of 1, 1 take away 2, you get -1. And this guy here is 3 lots of 1, take away, you get 2. And the coordinates of where you finish are 2, 4, 8, 16, take away 4 gives me 12. And 2, 4, 12, take away 1 gets me 11. Are you happy about what are called position vectors? Technically speaking, I should call it that. But position vectors are a vector where you start at the origin and go to it. So you can see that's the coordinates. If I was being really lawyer-esque about it, these guys would be written down in that notation. But I like coordinates, so I'll keep it. Now the hard part. We have to find the potential function. We know that it has the property that its gradient, which is the partial derivative with respect to x, partial derivative with respect to y, is equal to f. So in this case, it's equal to that guy, and it's equal to that guy. And we are now going to essentially do integration and work backwards. And I think I should do it up here. The partial derivative of the potential function little f with respect to x is x squared y cubed. So if I want to find f, I integrate that with respect to x. We did one shot at that yesterday, so here goes. You add 1 to the power and you divide by the new power. You all comfortable with integrating with respect to x, right? You treat y as a constant. And then normally you would say plus c, but in this world, when x is a constant, right, when x is a variable, your constant is some function of y. Now, 9 times out of 10, that guy's just going to end up being 0. But occasionally he is something. So it's a good idea to put him in just for the, the times where that does become more important. Move on now. And I'll write down the f of y has to be equal to this guy. And if I integrate this guy, I get 1/3 y cubed x cubed plus a constant. If you integrate with respect to y, the constant is a function of x. And now what you do is you merge these two pieces of information together. And you try and find a function, the simplest one that's possible, that these equal each other. Don't overthink it, because most of the time it's going to be what you think it is. Would you agree that f equals that guy works for both of them, especially if you make these two constants 0? Does that make sense? That if f is this guy and f is this guy, if you look at these, aren't they the same thing, right? And these two can just disappear as plus 0, which happens a lot of the time. I now know my potential function. And according to the fundamental theorem of line integral, then, I can find the line integral of this guy by just finding the value of the function at the end, which is 12/11, take away the value of the function at the start, which is -1, 2. You see, I just evaluate this at the beginning and at the end, right? I don't evaluate it at t equals 1 and 2. I evaluate it at the coordinates at t equals 1 and the coordinates at t equals 2, right? I guess that's saying the same thing. So if you do 1/3 12 cubed times the 11 cubed, take away 1/3 -1 cubed times 2 cubed, we should be good.
Don't you have to prove that it is conservative?
Yes. Technically speaking, yes. But we'll assume that somebody else did it. And you're not asked to do it in the homework after the first few questions, so we're not going to do it. But yeah, technically you should. If somebody just threw one out in front of you, you better check it. Because if you don't do what I just, if you don't check it and you go through this process, you may get a number, probably will. It just won't be right, right? It won't be the correct answer. Analogy. Do you know if you do L'Hopital's rule when you shouldn't, don't you get a number? It's just not the right answer. Right. So you can apply it. So back to this fella. What have I got? I got 1/3, put a bracket around it for safety, times 12 cubed times 11 cubed. Take away 1/3 in the bracket to be safe again, times -1 cubed times 2 cubed. And, oh, that's probably not going to be a very nice decimal, but I do know what it is. It's that guy. Ugly answer, but it is what it is. That's going to be the gist of what we're going to be doing all day today. We are going to be finding line integrals. We're not going to test that they're conservative. We'll assume that that's true, right? That's why they gave us the question. And we're going to find the start and finish coordinates. We're going to find the potential function. We're then going to evaluate the potential function at the end, take away the value of the potential function at the start. Horrible calculation, get an answer.
Are we going to be doing ones that g of y and h of x are not 0?
There are some that happen to do that. You're right.
Okay, because that's freaking me out for some reason.
Oh, well, maybe I can find one that's got one.
Okay, thanks.
Question 6. Does that have one? No, I don't think question 6 has. 7 doesn't for sure. 8 doesn't for sure. Don't know about 9, hard to tell. 10, be very doubtful. 10 might have one. I won't do 10 yet because there's a lot of things we need to fill in, but I think I should be able to get one by the time we get there. And if not, I think 10 will have it. You kind of don't know until you do it whether it's going to happen or not. The difference that I'm going to do with the next question, which is actually going to be question 6, is that we're going to up the ante. The vector function is now going to be 3 guys. It's going to be x, z. No, darn it, that's me and my scanning. I apologize. Y, z, x, z. And then x, y plus 12z. Now, this is a conservative field. If you want to prove it's a conservative field, you have to do a much more messier test that I won't show you because you don't need to know it. But eventually, you know, you can look it up and find it. We are assuming from now on that they are conservative. So, what's this guy going to look like? Well, it's going to be the usual standard fella that looks like that. And C is the line segment joining the point 3, 0, -1 to the line to the point 4, 5, 1. Now, in the olden days, wouldn't I have to find the equation of that line as a parametric and do a whole load of other stuff? But actually, haven't they just told me A and B? Right? So I'm getting A and B for free this time. Let's find the potential function now. F of x, f of y, f of z is equal to, if I stick to my notation, this guy's called P, this guy's going to be called Q, and this guy's going to be called R. So it's going to be YZ, XZ, and XY plus 12Z. Oh, this one might have one of those things you're hoping to see, Tessa. Might have, that could cause it. Right, start with the first one. I want to integrate YZ with respect to X. Don't overthink this one. No, the answer's not 0, that's differentiation. But what's the integral of YZ with respect to X?
X.
Just X or XYZ?
XYZ.
Which is probably what you meant, right? Now, plus a constant, right? You're going to have a little problem with this. If you differentiate or integrate with respect to X, the constant is in fact a function of Y and Z. That's basically just a little placeholder to say there might be some Y's and Z's in your final answer. Right now, we don't know. The second one was that one. If I integrate this one, would you agree you get X, Y, Z plus a function and a constant? Doesn't need to be that guy, but it will be a function of, what's that going to be? X and Z. And then we'll take the last one, which is XY plus 12Z. And if you integrate this one, you get XYZ plus what? What do you get if you integrate 12Z with respect to Z?
60 squared.
Okay. Plus, I'm running short of letters of the alphabet, a function of X and Y. Now, let's show you how you put all that information together. Would you agree that all three of them have an X, Y, Z?
Yep.
Would you agree this one has a 6Z squared? This one doesn't, and this one doesn't. But couldn't 6Z squared be fitted into this placeholder? Isn't that a place to catch these guys? And so your answer is that. Now, that is the correct answer for this, but let's just pretend that this guy was X, Y, Z plus X squared, right? And some stuff, and this one was plus 3Y squared and some stuff. Wouldn't the answer be X, Y, Z plus an X squared plus a 3Y squared plus a 6Z squared? You see, when you, so these little guys are just placeholders to keep yourself legal, right? There might be some other stuff that has the variable Y and Z in it, or there might be some other stuff with a variable X in it or whatever. And basically when you do it, in a way, what I kind of do in my brain is I ignore all that, and don't you just merge everything together? Right. Does that help? You're nodding a lot. I like nodding. Does that mean, okay, it's not as weird as I thought it was going to be?
Yeah, exactly. Thank you.
Right. Okay, so we got this guy. Then we should be able to get the answer. The line integral through the force field F from the point there to there is going to be the potential function at B, take away the value of the potential function at A. In this case, it's going to be the value of the potential function at 0.451, take away the value of the potential function at 3, 0, -1. And what do we get? We get 4 times 5 times 1 plus 1 squared. No, it isn't. Plus 6 times 1 squared, that's better. Take away 3 times nothing times -1 plus 6 lots of -1 squared. So I get 20 plus 6, and I get nothing plus 6. And so I get the answer 20. Oh God, I got it right for a change. I'm on a roll here. It's 20. You could think of this as the work done in traveling through a windstorm in 3D, right? That had this vector field describing how the wind was blowing, right, at any given point, and you're traveling through it, and it would take you 20 units of work, whatever units of work are, to do that job, right? So you're, it would cost you energy to do that, right? The wind would be against you in some way. Even if you're getting a little bit of a push somewhere, aren't you going to hit a wall somewhere else and it takes more energy? So the net effect is that. I'm getting better vibes today than I did at the start of yesterday. I think I tried to do too much at once. Do you feel the process has got a B, C, D kind of look to it, right? Well, and actually, I don't need to worry about 10 now, right? We've seen one. We might do 10 anyway, but we don't need to worry about it. Let's jump to something with other things in it. Question 8. We're going to do, not 8. Oh God, I should put these in order. I probably will. I want to do some RDR things before I do any of the others. Right. I'm scanning through here and I've got a whole load of questions testing, is it a conservative field or not, which is fine, but I want to do a ... guy. Okay. Sorry for the jumping around. Once today's finished, I'm going to go back and reorder these questions so that they kind of make more sense, because they are. So I know this is just back to front, but this is the first one I found that I like. So F is going to be y squared cosine z, 2xy cosine z, and it finishes with a negative xy squared.
Is that a 2 or a z in front of the xy in the second bit?
There's a y squared cos z, that's a 2, so 2xy cos z, and
That's
that's
what
a
I wanted
negative.
to know. That's the one I was
Yeah.
asking.
Yeah, my 2's look very like z's, so watch out. My z's have little strokes through them. That's kind of how I compensate for that. The curve that we're going to be traveling through this thing, the space curve, is described as t squared sine t, and the journey starts at 0 and the journey finishes at pi. So that's the information. We're going to be asked to find the line integral like all the other ones. By the way, this is, I've probably mentioned this, but this is not going to be in this week's homework because we won't get it finished today anyway. It was never going to be anyway. But I will leave it open for you to, get a head start on next week's homework. And obviously this stuff will not be in the test either. Right, back to this one.
So the quiz is just change of variables, line integrals, and 16.1. I can't remember what that was.
I will take your word for it. I don't have it in front of me, but it's whatever website says it is, because I think there's 2 or 3 sections. Right, let's find out the A and the B, right? The coordinates of where it starts and where it finishes. If you plug in 0, you get 0. Oh, sine is 0, 0. So you get 0, 0, 0. And if you plug in pi, you get pi squared 0 pi. Okay. Got my start and finish. Let's find the potential function now. And it's going to have an x, it's going to have a y, and now it's going to have a z. And this fella is y squared cosine z, 2xy cosine z, and the third one is going to be a negative x y squared sine of z. Start with the x's, and that's y squared cosine z. So that makes f xy squared cosine z plus some function that doesn't have x's in it. So that's my placeholder function. Then I'll move on to the second one. And when I integrate this one with respect to y, that's the only guy that's a variable. So you add 1 to its power and you divide it. And it's kind of nice to see this. Do you see that you basically get that guy again? Plus, whatever letter of the alphabet I'm using right now, anything that doesn't have a y in it. And then the final one, the z one, is negative x y squared sine z. And I'm going to integrate it. And if you integrate a sine, don't you get a negative cosine? And so you end up with plus a function that doesn't have a z in it. Now, when we look at the pieces, isn't this a nice easy one? Because that's all you have. If there was a plus y squared left over, wouldn't I join that to my group? If there's a plus x squared, I'd join that to my group. So we are looking at our function, our potential function is just made up of that piece. And to get the line integral, we find the value of the potential function at the end and the value of the potential function at the start. So it's going to be the value at pi squared 0 pi, take away the value of the potential function at 0, 0, 0. If you make that pi and you make that 0 and you make that pi, you get a whole load of nothing. And if you make that nothing, nothing, and nothing, you get a whole load of nothing. And so the answer is nothing. And I am in a roll because that's the right answer. Rosie, question.
In your potential function, you have x squared, y squared cosine z. How did you get x squared?
I didn't. It should have been x, but the good news is it didn't cause any trouble.
Okay, thanks.
Can we pretend that I had a function, and when I did the x, the y, and the z, I got the following? Just for argument's sake, right? Based on what I have got here, what would the potential function be?
X squared y cubed plus x minus y squared plus 2z.
And aren't they just the placeholders for the bump, bump, bump? Just wanted to emphasize that one more time. Are these looking much easier to do a line integral using the fundamental theorem than it was, 2 days ago when we had to do a whole load more work, in my opinion, to do that? Where are we going next? Yeah, let's try this one. It's 19 or 18. Which one looks more interesting? 19 is better because it's 3. I think it's easier. Well, it's more interesting to do 3. Okay, 19 it is. And it's 2xz. Wow, okay. 2xz, 2xy, and x squared plus 9z squared. And the curve C is the parametric. I'm writing it down parametric. They're giving it as x equals y equals z equals, but I'm just going to do it this way. T squared, t plus 2, 3t, take away 1. And they're doing the t like that. So let's do the start and the finish. If you plug in 0, you get 0, 2, negative 1. So that is the coordinates of the start. And it goes through this force field and it does, it does its little curvy thing. And then it finishes at t equals 1, which is 1, 3, 2. So, are you comfortable that when you know the space curve in the start and finish, isn't the coordinates of the start and finish pretty easy to find? Right, just plug and chug. Right, now we'll go hunting for the potential function. So f of x, f of y, f of z is going to equal that guy, and finally that guy. Now, if I integrate this fella with respect to x, I get x squared z plus a function that doesn't have x in it. We do the second one and we integrate it with respect to y, I get what do I get?
X y squared.
Yeah, for some reason my brain wasn't working. And a function that doesn't have a y in it, so that would be some x and z's, I guess. And then the last one of the set is x squared plus 9z squared. And if you integrate this guy, you get x squared z plus add 1 to the power and divide by the new power, that guy. And our constant is anybody who doesn't have a z in it. Okay, now it's merge time. That, and that. What's the potential function when you merge those three together?
X squared z plus 3z cubed plus xy squared.
I agree. I just wrote it slightly differently, but she's right. We all agree? And those placeholders now are just an inconvenience to us now. You have to write them because it's part of the proof, but they don't. Yeah, they don't bring much to the party, do they? Except keep everything correct. So this fella, the line integral, is going to be the value of the function at the end. Take away the value of the function at the start. So it's going to be the value of the function at 132. Take away the value of the potential function at 0 to -1. Okay, that's going to be fun. Okay, so it's going to be 1 squared times 2 plus 1 times 3 squared plus 3 times 2 squared. Take away. Nothing, don't care what that is anymore. Nothing, don't care what that is anymore. And 3 times -1 cubed. Are we cool with that? Okay. 2 odd 9 odd 12. That's -3. Take away negative, you add a 3. That looks like we got 21, 2, 3, 4 to 5, 26. No, I screwed up. Okay, where's my counting gone wrong? The answer I can see the answer is 38. But where did I
How did
screw
that
up?
3 times -1 to the third become a positive 3?
Well,
Oh, no, I
-1
figured it out.
cubed.
Never
That's
mind.
positive 3. I need to get 38 out of this, and this is.
I think you're 3 times z squared cubed. It should be 3 times z cubed, and you did 3 times 2 squared.
Oh, this should be a cubed.
No, yes.
Ah, and that gets me 24. And the 24, 25, 26, 27, 28, 29 gets me my 38. We got it. It's 38. That wasn't too bad. Don't really like any of these. Pretty boring. Anything here different? I want something different. Okay, I'm going to have to go back to 2-dimensional. Showing away is a lot easier to do because there's less work. No particular reason. 17 will do. This fella is 5xy squared. And this guy, no, I'm not doing that one. That's too easy. All right, let's find a different 2D one. Okay. Oh, okay. Do 15. At least it's got something different in it. This guy is very easy, so I didn't pick it because of that. I probably wouldn't have chosen, but I did pick it because of this. You're traveling along the curve y equals x squared, and you're going from the point -1, 2 to the point 2, 8. Well, haven't you basically told me the coordinates of A and B? So I can just go straight into finding the potential function. This guy here is going to be x squared, y squared. So we have that guy, and then we have that guy. If you integrate this fella with respect to x, you get 1/3 x cubed plus a function that doesn't have any x's in it as your constant. And if you do this one and you integrate it with respect to y, you get 1/3 y cubed plus a function that doesn't have any y's in it. And when you merge those two together, your potential function is 1/3 x cubed plus 1/3 y cubed. Agree? And to finish then, the line integral would be the value of the function at the end, which is that guy, take away the value of the function at the beginning, which is that guy. And so we get 1/3 times 2 cubed plus 1/3 times 8 cubed, take away 1/3 times -1 cubed plus 1/3 times 2 cubed. Oh, that's going to be a challenge. 2, 4, 8/3. It's 256/3. That's -1/3. If you subtract it, you add it. That is 8/3, and you subtract it. I get 26/3. What's wrong? Oh, that's what's wrong. 256. I get 257/3, which is 80, whatever. That's still wrong.
A cubed is 512.
Okay. So I get 513/3. Let's see if that is something nice. Oh. Yep, that's the right answer. Yeah, we have enough time to do something
I
wrong.
love that little trick for figuring out if a number is divisible by 3 or 9.
All the digits add up to multiples of 9 or multiples of 3.
Yeah, it's a fun trick.
Yes. Should have paid attention to it, but I didn't. Let's do the thing that scientists do, or more particularly engineers do. And they have a force field. And that's P, and that's Q. And I'm going to do the partial derivative with respect to y. And I'm going to do the partial derivative of this one with respect to x. And you do this one, you get 2y. And you do this one, and you get 3. Would you agree that that is not a conservative field? But I'm going to pretend that I didn't check. And I am going to do the process as if it was a conservative field. And let's assume that we're going to do it from the point A with coordinates 1, 2 to the point B with coordinates 3, 4, right, just for argument's sake. Then that has to be true. And this has to be true. So the partial derivative with respect to x has to equal 2x plus y squared. Agreed? And if you integrate it, you get x squared plus y squared x plus some function that doesn't have an x. So some function of y. You then go into the second one, which is this guy. And you integrate him with respect to y. And you get 3xy plus 1/4 y to the 4 plus some function that doesn't have y's in it. And you merge them together, and your answer is x squared plus y squared x plus 3xy plus 1/4 y to the 4. Great, that's how you would tackle that situation if they were conservative fields. Agreed? Merge them together, right? And then you would finish and you'd be able to do a calculation that is the value of the function at the end, take away the value of the function at the start. In this case, it's at 3, 4. Take away the value of the function at 1, 2. I'm not even going to calculate that. I'm just going to pretend I know the answer is 100. Don't really care what it is. Can you see that you can go through this process and get an answer? That answer will not be correct unless by a fluke of randomness you got 100 in the real way. If you had to do this particular one the right way, you would have to find out how those 2 points, let's pretend it went like that, a straight line. You would have to find the equation of that straight line. You'd have to do all the usual stuff, right? You'd have to do it Wednesday's way, right? The way you were showing on Wednesday, right? And that would have been the correct answer. If you had done it the fundamental theorem way, that would be the wrong answer. So I said today, and I'm sticking to that, that we are assuming that all the questions in the section that we've been doing today are all conservative fields. But can you be careful that if you ever do anything, any calculations, and you know you're doing line integrals for whatever reason you're doing them, always do a check to make sure it's conservative. Because I don't want you to build a bridge and think something's 100 when it should have been 500. Because to quote an engineer professor that's left now, Professor Brown, he says, I'm very particular about my engineers getting things correct because I have to drive on the things that they build, right? So we don't want anyone to screw it up. Now, why can that? I can imagine all sorts of science. Can you imagine somebody in NASA just doing their usual calculations? Oh yeah, I've got a little line integral here, blah, blah, blah. The answer's 100, they plug it in and bad things happen. So we are breaking my own rule that when we do these questions, that they are conservative fields. And the reason we're doing that is to save time. But really in the practical world, you should do it.